Welcome to the communication system playlist. So in this section we are going to discuss about the quantization, basics of quantization levels, and the working of the quantization. So as I said, today the title of the topic is the basics of the quantization. So the function of that is to convert the analog signal into the digital data. If we want to write the block diagram of the quantization, the block diagram consists mainly on three blocks. First one is sampler, second one is quantization, and the third one is encoding. So the input of the sampler is always analog signal. So what does that mean? Analog signal means that the time characteristics of the analog is continuous, as well as the amplitude of the analog signal is also continuous. So when you pass that analog signal through the sampler, and we have already discussed what this sampling mean in our previous lectures. If you want to understand more about the sampler and the working about the sampler, you need to see our previous lectures. So the sampler will quantize or discretize the time characteristics, like the output of the sampler will be the sampled version of the analog signal. And what does that mean? The sampled version of the analog signal, mt, you can write it as m of n, and the time characteristic is discrete, but the amplitude is still continuous. For example, if you have a continuous or analog signal m of t, that is sine 2 pi ft, so it means that for any value of t, like continuous t, 0.1, 0.13, 0.17 and so on, you can have a continuous value of the amplitude. So maybe through 0.3, 0.4, 0.5 depending on the signal level. So when it passes through the sampler, the signal is discrete. In that case, m of n, which is equals to sine 2 pi f and n ts. And ts is basically equals to 1 over fs. So you can say, so ts is equals to 1 over fs, and fs is the sampling frequency, which is equals to or greater than twice of the analog or continuous or modulating signal frequency. So for this you can pick any value of n, so that is 1, 2 and 3. So you can choose the discrete value of n, but still you can have the continuous value of the amplitude. So you can have the continuous value of the amplitude. So when you pass that through the quantization, so after that the quantization will discretize the time as well as amplitude. So after passing that, you will get a digital signal. So that means that its characteristics mean the time will also be discrete and the amplitude will also be discrete, and you will end up with the digital signal. And when you pass that digital signal through the encoding, you will get your data in the form of digits, like something like that, 10, 10, 10, 10 or something like that. So this is your digital data. So let's first understand the working of the quantization. So for the working of the quantization, we will first take this red signal. So this red signal is a continuous signal, or you can say this one is the analog signal, and then you are sampling it. So these are the samples, sample values, and these are the levels. So you are sampling the signal at a particular point. Let's suppose you sample at that point, you sample at that point, you sample at that point, and then you sample at that point. Similarly here and there. So it means that you are discretizing the time index, but you are getting the continuous value of the amplitude. So to discretize the amplitude, you need to suppose you need to take some bits to represent the quantization level. So for this particular example, we choose n is equals to 2 bit. So if you choose n is equal to 2 bit, you can define the quantization level, which is equals to 2 raised to the power n. Here in this case n is 2, so 2 raised to the power 2 is equals to 4. So 4 is our quantization level. So you can see 2-bit. So 2-bit means combination of 4. So here you assign this as a 0 0. So you assign minus 0.5 1 0 1. You assign 0 as 1 0, and then you assign 0.5 1 1. So you assign the bits to each amplitude level, and the range of the continuous signal is from maximum, or x max is 1 and x min is 0. So the range is 0, and the step size, you can calculate the step size. So x max minus x min, so x max minus n min. So step size means from here to there, here to there, and then here to there. So there are 4 steps or 4 level for this particular example. So x max minus x min divided by L. So L is equals to 4. So maximum is 1 minus minimum is minus 1. So it means that 2 divided by 4, which is equals to 0.5. So here you can see, so the 0.5 0 and then minus 0.5 and then 1. So to discretize the amplitude, you need to get the nearest value. Suppose this sample is maybe at the particular level is 0.7 or 0.74. So its value is 0.74, but you are taking the nearest value of the amplitude so that you can choose the quantized result. So from here it is 0, and then from here to there, so it means that it will take the nearest value is 0.5. So it will take the nearest value 0.5, and then from your next sample, this one, so this one is 1, but the nearest value is 0.5 here again. So it means that from here to there is 1, and then from here, so this one is again, so this is, you can say 0.75 approximately, but the nearest value is 0.5. So that is why this level is again up to here. So here, and then so the next sample is 0. So it will keep continue and like this, and the other sample is 0. So this one is 0. So the 0, the nearest value is still 0, and then you can see the next sample. So next sample is that one. So it means that's 0, and then so the negative minus 0.707 minus 0.707 approximately, you can say 707, but the nearest value is 0.5. So you can have 0.5. For this again you have nearest value 0.5, and then for this again maybe 707.707, the nearest value is again this one, and similarly for this one it has a something like that. So this is the basic, this is basically that you are ending up with this type of curve that you can have. So you can have this value, maximum value, like from here, because you have chosen 0 0, so that is why you have to go here, and then from there to there. So because we have chosen this level as a 0 0 as well, so from here to there, and then from here to there, and then from here to there, and then from here to again there. So this is basically, we are basically quantizing the amplitude. We are basically getting the nearest value of the amplitude. Like if we want to understand, we can draw a table for this figure. So the first one we can write the sample value. The second one we can write the nearest value or the quantized value x cube. The third one is the digital signal that we give the digital data that we assign bits, and the quantization error. The first one was 0, so that is why the nearest value will be 0. So as it is 0, so we assign a bit 1 0, 1 0, there is no quantization error, because the quantization error is x cube minus x. The second was, it was approximately 707. It was approximately, you can say, so this value is 0.707. So you can say 0.707, but you assign the nearest value, which is 0.5, and the bit was 1 1. So bit was 1 1. So you have a quantization error. So 0.707 minus 0.5, the answer is 0.207. You have quantization error. So the next sample value is 1, the nearest is 0.5 and you assign bit 0.511, so the quantization error is 0.5. Similarly, so this way on, and then you can see on the negative side here, so minus 0.707, so that one is minus 0.707 and the nearest value is minus 0.5 and you assign bit 01, so you assign bit 01, the quantization error is always positive because it is error, so it doesn't matter what is the negative value or what is the positive value, the error is always negative. The error is always positive. The difference between these two values will give you the quantization error. Okay, the difference between the amplitude of these two values. The other one is minus 1. So the other one is minus 1 and then you assign minus 1. You assign minus 1 and then the bits is 0 and there is a 0 quantization error. So that is why you can calculate the quantization error. So let's have a particular parameter. So we have some few basic parameter of the quantization. The first one is the dynamic range. We have already considered the number of bit n. So n was number of bit. The quantization level was L. We have already calculated L. The other one was step size and then we have already defined step size. And after that we have quantization error and then we have a dynamic range. What is dynamic range? It is the ratio of the largest to the smallest measurable amplitude. So largest amplitude to the smallest amplitude. So if we see this particular diagram, we can say that the largest amplitude is 2 raised to power n minus 1 and the smallest amplitude is 2 raised to power minus 1. So if you simplify this, you can have 20 log 10 2 raised to power n, because when so base is same, so it means that the n minus 1 and then plus 1, so this will be cancelled, the remaining is 2 raised to power n, that is this one. So if you this is power, though it will come in front of that, so n 20 log 2, so this the answer of 20 log 2 is, so this one 6.02 into n, and is the number of the bit. So this is the dynamic range. The other quantity is the SNR of the quantization. The definition of the SNR, so it is 20 because we are representing the parameter in terms of voltages, not the power. If it will be power, then here you can write 10, but if it is voltage, you can write it 20. So 20 log 10 signal RMS voltage divided by noise RMS voltage. For noise RMS value, you can say the quantization noise mean square error, you can define that, is equals to 1 by its step size and q square dq and the range of del by 2. So so that is basically the always the del by 2. So the range is upper limit minus lower limit. So if you integrate that, so integrate means you increase the power upstairs and then increase the power downstairs and write the upper and lower limit. And then if you simplify this, you will end up delta square by 12. So for the noise RMS value, you are taking the under root, so the square will go on and then you will end up delta by 12 under root, which is equals to 2 and then 3 under root. This is equation 1, that is equation A. Signal RMS value, so we have full scale voltage, which is V max minus V min. So the peak voltage will be full scale voltage divided by 2, and if you want to write in RMS value, you will divide with the 2 under 8, so additional quantity is the 2 under 8. So it is better to write the RMS peak value in term of delta. So because your noise is also in term of delta, so you need to also convert the peak signal in term of delta. So delta is equals to V max minus V min divided by L. So L is equals to raised power n, and V max minus V min is equals to V full scale voltage. And then if you rearrange this equation, you can say that okay, full scale voltage is equal to delta, so this will go here, delta into 2 raised to power n. So signal RMS voltage is equals to, if you insert this value here, so if you insert this value, if you use this value here, you can say the RMS value is 2 raised to power n delta by 2 under root. So this is 2, this is 1, use both equation in A. So you can write the SNR. So SNR means signal voltage divided by noise voltage. So this delta will be cancelled with this delta, this 2 will be cancelled with this 2, and then you have 20 log 2 n, and then 3 will be upstairs and then downstairs. So you can write in term of sum using the logarithmic rule, and then this is first term, so which is the dynamic range. We know 6.02 into n, and the value, if you calculate using your calculator, the value is 1.76. So that is the SNR. So the other one is uniform, but the quantization is non-uniform and uniform. If it is non-uniform, so the amplitude of the quantization or amplitude level is not fixed. The amplitude will vary. But if you have a uniform quantization, so it means that the amplitude will remain fixed. So for the uniform quantization, we have two types: mid-trade quantization and the mid-riser quantization. So this is the curve of the mid-trade, like so, something like that, and this is the curve of a mid-riser quantization. We will try to explain this type of quantization in our next lecture. So I hope you understand this lecture very well, but if you still have any question, you are most welcome. Write the question in the comment box. Thank you for watching.